Hello, how's everybody doing? So, this is Stefano from Eurotech. I'm Dejan from Red Hat. We've been working a lot lately on these IoT backend components and trying to put together an IoT cloud at Eclipse. And today we would like to talk more about projects like Kapua and Hono and see how they can help achieve that goal.
So before start talking about the Eclipse IoT cloud tools and frameworks, let me just set the background and the scenario where this kind of applications are used. So IoT embraces a wide range of concepts, scenarios, technology stacks, tools, infrastructure, whatever. So even it involves a lot of different stakeholders, and often these stakeholders have different perception on the value that the solution has to provide them. So let's start from a real-world scenario. Okay, so the picture describes a typical scenario where we have the field devices and on one hand and the enterprise applications on the other hand. So the problem is bringing the data from the field to the back-end applications. For a general IoT scenario, we have a diversity of devices, different kind of devices. Typically, there are devices that could be connected to the network because they have enough computational power. There are devices like meters they don't have. You have to connect them to a gateway that enables the transmission of the data through the network. We have multiple protocols even, both at the transport level. MQTT is one, AMQP is another, co-op also. And we have multiple protocols also at the device management level. CURA is one, but lightweight M2M is another. Typically, devices are geographically dispersed, so the only way or the most impractical way to connect them to the backend system is to the public network infrastructure, which means basically internet. And scenarios could range from a small amount of devices to a large amount of devices, and application that manage these things have to scale with the number of connection, the number of devices that are connected. Even more, we have diversity of information consumers. We may have enterprise applications applications such as, for example, ERPs, data analytics system, business intelligence, dashboards, whatever application may need to extract value from the data transmitted from the devices. Also, we have to provide quality of service. Those kind of applications have to be up and running absolutely 24/7, and performances have to be adequate for treating all this data. And security at every level. So you need to assure that the data integrity all over the chain of information, the paths that the information follows, and you have to assure that nobody except the owner of the information can access the information or disclose the information that is transmitted. So for decision makers, such a scenario could present challenges, and they may perceive barriers. Many challenges are seen as or sound as reasons for not implementing IoT solutions. So we have a complex technology. We have specific know-how required, so it means that if you don't have skills in the company, you have to provide somehow. And you have infrastructure required because of that 24/7 thing that I just said. You need to provide systems that are up and running continuously and perform perfectly. Then you have to manage IT and OT challenges. OT deals with management of devices on the field, which is something different than IT. Security, we already said. Regulatory issues and certification. Some business scenarios requires them by law. You have to conform or you have to be compliant with regulatory and certifications. And you also need interoperability of solutions. You don't want your solution to work with just one or a couple of consumers, but you want to make as many consumers as possible to access the information. So the point is, what are the pitfalls that we should avoid and the solutions that we can put in place?
Yeah, so usually, I mean, it's a complex problem to solve, right? And we see people over and over creating basically a silo applications, solving recurring problems over and over again, and ending up with solutions that are hard to upgrade, hard to maintain, solutions that don't scale after a while, and where security is usually implemented as an afterthought, right? So what's the solution to this is to basically an attempt to build a well-maintained open source stack within a well-governed Eclipse IoT community, right? And provide all the building blocks and components for people to be able to create scalable, secure, and maintainable IoT backend stack, right? And with a stack like that, developers, in the end, should be able only to focus on their devices and on their backend applications, and having all the infrastructure basically put in place properly. So the stack here is basically a three-way stack and something that we talked about more. So we have a Eclipse Cura as a device gateway layer, and we won't talk more about Cura at this session because it will be covered in other sessions. What we'd like to focus on is the Eclipse Kapua project and IoT integration platform, and what problems the Kapua can solve for you. And after that, we will focus on Eclipse Hono as a device connectivity layer, and see how Hono can help solving some of the connectivity and scalability problems of such IoT solutions. So I'll let Stefano now walk you through in more details through Kapua.
Thanks. So Eclipse Kapua is just it's a newly contributed project in the Eclipse Foundation, and the goal of this IoT platform is to provide a modular integration platform for implementing end-to-end IoT solutions. So it provides a multi-tenant environment natively and focuses on providing comprehensive management of edge devices. But it also supports storing data in a data store, as well as supporting message routing for real-time data processing. It also provides a web-based administration console for users, but most of all, it implements full programmatic access through RESTful APIs. That means you can build on top of Kapua. You can build your own application. You can take advantages over the services that Kapua implements. So let's take a look at the building blocks of Kapua platform. So starting from a field perspective, a device establish a connection with the device connectivity layer. Actually, we have currently we have implemented MQTT as transport protocol, but we want also to provide support for other protocols, COAP and AMQP, among others that are important in the IoT context. Once the connection is established between the device and the platform, messages start to flow from the field to the platform. So we have basically three kinds of messages, three broad categories: lifecycle messages, command and control messages, data messages. Data messages is those carrying the telemetry data, whereas the lifecycle and the command and control are used to manage the system. So as long as a message hits the message routing service, then it is redirected to the proper consumer. So first of all, we have the device registry. Device registry keeps track of the connection between of the connection status of the devices, and also keeps a log of all the messages, lifecycle messages exchanged between the platform and the devices. And it also holds a profile for each of the devices that have been connected or are currently connected with the platform. Device management is about managing devices from the platform, remotely managing devices from the platform. Currently, we are supporting the Cura device management protocol, but we want to support even more in the future. I'll talk about this maybe later with the last slide. So for the device management, we implemented, we have already contributed 4 basic management service. So we have the bundle service to retrieve the bundles that are installed in the Cura device and start or stop a bundle in the Cura device. We have the command service that allows the platform to send shell commands to the device and ask the Cura device to execute these commands and then send back the output to the platform. Then we have configuration service. Configuration service allows to inspect the configuration of applications inside the Cura device and allows you to change and send the changes back to the device in order to control it. And then we can upload or update bundles or software in the field gateways through the package service. So then the other big piece is data management. So data management allows to store information in a NoSQL database. Basically, you have to ingest data at an high speed and make it available for later processing by third-party application. And it also provides, supports a real-time event engine that allows to process messages on the fly and trigger actions on when certain conditions are met by the message. All these services are built upon a strong security layer that allows for management of every resource available in the platform. So first of all, the account management, which means multi-tenancy, and then establish permissions, so access control and identities. So for the administration of the platform, a web console is provided, but every functionality that a user can access through the web console, he also can access through the REST API. So you can build your own administration applications on top of it. And through REST APIs and real-time rule engine, you can also integrate at the application level with accessing the data, retrieving the data, or processing the data in a real-time way. So that's basically the building blocks. So with this slide here, we just it's just more a detailed representation of all the services that we have provided. The darker blue boxes are the ones that are already, that will be provided for the first release. The lighter blue boxes are services that will be added later in the roadmap. The nice thing, we represent devices as boxes because they are really independent one compared to the other. Devices can and should interact between, but only through the REST API, and there's no shared context between them. So this allows to provide different implementations of a certain service, and provided that this implementation conforms to the API of the system, it seamlessly works with all the other services in the platform. So this is modularity plus flexibility. So the basic technology stack for service implementation. A Kapua service is based on a Java 8 virtual machine. We have some third-party libraries that help to manage common tasks, and then we provide with those blue boxes here, we provide some helper project that allows to make the implementation easier and faster. The Kapua locator is one important box that it is the mean by which services can locate other services, obtain references of the services, and invoke operations of the services. For persistency, we're using JPA, we are using Eclipse Link implementation, and in the first contribution, we are using H2 database, but thanks to the JPA abstraction layer, we can even support other database. For all the serialization stuff, we are using JAXP with Moxie, and we are using also dependency injection with Juice. For the security stuff, we are using Shiro, but it is pluggable. It can be substituted by another framework. So this is basically the taxonomy of service implementation in Kapua. So when it comes to the deployment, what we see is a differentiation between the front-end services and the back-end services. So front-end services expose services to outside. We have the application console, as we said. We have an AP gateway for programmatic access to the platform, and we have messaging. All those use the Kapua locator to find the back-end services here, retrieve references, and invoke services on them. So the modularity of the platform allows for different deployment scenarios. So what we provided for the first contribution is basically a scenario where the application console and the backend services are tied together in the same, are executing together in the same virtual machine. So the same is for the API gateway, and the same is for the messaging, which is basically a message broker. But we can even support more complex scenarios. So thanks to the modularity of the architecture, we may imagine a scenario where each backend service is running on a different Java virtual machine, and it communicates with other services, and the front-end services through the locator pattern go to a discovery service, find a reference of the backend service, get the reference to the backend service, and then invoke methods on them. This kind of architecture is really fits really good. Let's say in a scenario where the microservices are deployed into a container, we can think we can exchange the container world with even with Docker. Docker is a container. So this allows the platform to be deployed in a variety of cloud providers and leverage all the orchestration and cluster management tools that are growing around this kind of technologies. Then for just a sketch, for device management, we implemented a layered approach. So abstracting the device protocol layer and the device application protocol layer. So here you can think about MQTT versus CoAP versus AMQP. Here you can think about CURA devices or lightweight M2M devices. And there's an abstraction over this layer that is the platform protocol layer. By doing this kind of layerization, we think we were able to implement the platform with different protocols underneath. So basically, I think this is all for the Kapua internals, I would say.
Well, it's not, because now we're going to talk about device connectivity.
Exactly.
So,
we're looking.
Yeah, looking forward. So, as Stefano said, like Kapua is developed to be scalable in terms of cloud deployments. But you know, the one piece that's, in my opinion, most critical in terms of scalability is that first device connectivity layer that we have there, right? And at this point, Eclipse Kapua, this first implementation uses MQTT protocol and Apache ActiveMQ message broker in that connectivity layer, and that works very well until some point. And for smaller deployments and even medium deployments, I think, you know, it's all fine and well. But you know, one of the goals for the whole IoT Eclipse cloud platform is to provide a cloud scalability. So this kind of architecture implements some limitations in terms of number of connections and destinations, which, you know, one single broker can handle. And there are other limitations too, like security in terms of in the connectivity layer is all tied to the broker addresses. Really, it's not tied to the IoT domain, and there's no any general purpose. It's all general purpose messaging, so there's nothing specific in the IoT in terms of message formats and things like that you know people will usually like to see in this layer. So this is something that is goal of the Eclipse Hono project is to provide a tailored general messaging for IoT solutions. So the idea is to solve all the recurring problems like horizontal scaling, provide support for all the protocols used by different people, so MQTT and LW, M2M, AMQP, and provide also a support for any basically underlying messaging infrastructure. And you know, design the system with scalability, multi-tenancy, and device-based security, like a, you know, first thought in designing a system like this. So Hono is designed with the AMQP 1.0 protocol in mind, and there's a couple of reasons for that. Like MQTT, AMQP 1.0 is a standardized protocol, which is a good thing. People usually like standardized protocol, which means, you know, they have options. And there are a couple of features that I would like to show you about AMQP protocol that we think can solve some of the problems of the IoT connectivity. The most important one is that the AMQP, unlike other messaging protocols, is basically symmetrical protocol, meaning that there's nothing inside of the protocol itself that assumes client-broker kind of connectivity. So it's all just endpoints and connecting endpoints and exchanging messaging within them. And that means that we can now have different messaging paradigms inside of the messaging system. So we can have a traditional client-broker kind of messaging, but we can also have direct messaging and direct messaging. And as we will see in a couple of slides, this allows us to create a new horizontal scale topologies for the messaging layer that should provide a scalability needed for IoT. Also, AMQP provides its own type system, which, you know, if you first think about it, you can say, oh, it's too complex. Why do I need it? But if you start from any other protocol like STOMP or MQTT, you end up inventing your own type system. You end up putting things in protobuf or some kind of JSON and do all that kind of stuff. With type system embedded into a messaging protocol, you get your compatibility between different environments much easier. But it's not the only thing that's important about the type system is that, you know, the type system allows us to define basically a kind of a messaging API. And this is exactly what we need for this kind of system. So API, not in terms of programming language API, but defining the exact message formats flowing in and out from the HONO, and defining the message exchange pattern that we accept in this communication. And so far in HONO we defined four kind of APIs. It's like telemetry API, so we define how basically a telemetry message coming into a HONO should look like. There's a command and control API, there's a device registration API, and we defined an API for high priority events like device lifecycle events, something that we saw that services inside of Kapua usually use. So, as we said, important part of all this is scalable messaging, and the fact that AMQP is a symmetrical protocol allows us to create a new kind of messaging component that we didn't have so far, and it's called a message router. It's implemented as a part of the Apache Cupid project. It's called Apache Cupid Dispatch Router. And now, just to clarify what the router is, you can think about the message router as the same as a network router, basically. But just instead of routing TCP packets, the AMQP router basically routes AMQP packets, so routes messages and all the supporting commands there. So it's a big difference because the broker, message broker need to own the message. It's a store and forward kind of communication, right? So broker stores the message, confirms to the producer, then forwards message to the consumer, meaning that broker needs to have a lot of state in itself, so it needs to have a message store, it needs to know which messages had been consumed, hasn't been consumed, there's a transaction involved, so the message brokers are quite a stateful kind of piece of software, right? And as such, they are very hard to horizontally scale. Even if you put a lot of brokers in a scalable layer, you end up having a different kind of issues. Unlike that, a message router is a much simpler piece of software, so it's easier to scale, and it's ideal for a gateway into a messaging system because it can partition a lot of traffic and provide a scalable solutions. So, in our terms, combinations of the message brokers and message routers provides a very powerful toolbox in providing a scalable messaging solution that's needed for a very, very big and complex IoT deployment. So, in a nutshell, because we don't have too much time here, like brokers should focus on message storing and just keeping the stateful messages that needs to be reliably sent, and the routers basically should do all other work like connection scaling and traffic partitioning. So this is basically a picture of how all that HONO and scalable messaging can work together. So on the left side we have devices coming from all kind of different, using all kind of different protocols. Then we have protocol adapters for all the devices that are not natively AMQP. And those messages coming through the HONO server, sorry, which allows us to do a proper access control for connecting all these messages, and then messages are forwarded through the scalable messaging system, which consists of message AMQP routers and AMQP compliant brokers underneath, right? And on the right side, we have our IoT services, basically Kapua services can live all there and uses the same AMQP APIs, to access that device connectivity layer and consume all those messages as Stefano showed you previously. So basically, that's that's a short story. And you can see that, in our terms, we can see how, Kura, Kapua, and Hono together can provide a very powerful IoT platform, which we think can solve practically any IoT demands. There's a lot of work ahead, so all these projects are either in incubation or just had an initial code drop. So it's like really early days. So everything is done in open source. Everything is governed by Eclipse Foundation. Big companies like Bosch and Eurotech and Red Hat are all working on it. And if you're interested in this kind of software, now it's time to join the effort. Thank you. So, is there any questions?
Sorry, a few minutes late, but and sorry, you had to rush out at the end, but we certainly have time for questions. So.
Yeah.
Do you plan to bring all these own projects like Hono and all the stuff together into Kapua, or will they reside by their own? And will there be also a stack where Kapua and all the combinations will be together? How's the plan there?
We can see that they can work together and they can be used separately. So I think in the end, there's no hard decisions there made yet. And
So we have been discussing whether we want to create kind of a joint release, which is kind of a cloud stack, if you will, doing something like a release
train, yeah.
Project, so that we can make sure, okay, if you take these together in that version, then it will definitely work together.
Yeah.
But we're in very close collaboration with each other, so I'm pretty positive that we'll make that a job.
Yeah.
Because they have some kind of, how to say, overlapping 100%, but
exactly.
this is a little, could be confusing.
Yeah, we'll make sure that,
You still need to be able to use them individually and separately from each other, right?
Yeah.
So simply cutting out something from Kapua and replacing it with Hono does not really make sense if you want to run Kapua on itself. So
Yeah.
if you want to run Kapua without Hono, that should work as well, and therefore there is a little overlap.
And I think all this focus on a cloud deployment and being able to run like on Cloud Foundry or OpenShift should make easier for people to just set the things up and running and
Additional question. You mentioned in several parts that you have API, messaging API, different kind of messages like control, telemetry. Are those messages being defined by the same project, or you're taking that definition for all those standards? How it works?
what I showed was the Hono APIs where we define how AMQP messages should look when they come into Hono from the devices that maybe at some point would be Hono compatible, or from the protocol adapters, which basically converts messages coming from MQTT, converts them to Hono compatible messages coming into the system.
However, if you ask about the payload itself is done
Yeah.
by Hono. So Hono is completely payload agnostic. It doesn't matter what kind of telemetry they want to put in. It's just simply routed through Hono. Hono only takes a look at the header information, which is the meta information about what's the origin of the data and what's the destination and stuff like that.
Yeah.
We never look at the
Providing basic semantics for the communication, like addresses and basic headers defined there.
All right.
Thank you very much.